Okay, this is a recording because I saved it to the Zoom cloud, and Zoom cloud doesn't recognize that. Anyway, it's a long story, but the recording's lost. I should have recorded on my laptop. Anyway, so I'm just going to do it this way. Go quickly through this. At least it'll be like a video key. It won't be as good. We won't have the discussions as we did, or because I know I can't repeat that. Anyway, so here's the answer to one. We already went over these, okay? So I'm just going to go quickly through these. So I get this recording out tonight sometime. This one I put on there. It won't be on the test Friday. And I just put this on there because we're going to be getting into this kind of stuff more starting tomorrow when we do projectile motion. This will be the Y version of it. So projectile motion is basically just this is free fall on a conveyor belt. It's moving along in the X direction. It's still, but the Y part's still the same. Anyway, more about that tomorrow. Good chance that one like this will be on there because let's put it this way, it made the final cut. So I'll be adding it. It may get kicked out still tomorrow night. I haven't quite finished the test yet, but if I have room for it, I'll put something like this on there. And it's just using second green. Could be one like this because it's so quick, just half tau method. It's pretty easy. That's using timing or half tau to figure out the launch velocity. Okay, we already went over this one in class last week. But there will be an equivalent problem on there, something similar to this. Which you gotta do it. And, you can't do this one head to tail, of course. You have to do this one with components, stack and rack. So I roofs and J roofs. Remember that 600. So 600, and the angles are always going to be from the horizontal. So the J roof values will be the sine 600 sine or 400 sine 30 or 60, and the X values, the I roof will be the cosine. So you can always expect that on these kind of problems, that the angle will be from the horizontal. And then if your answer was 323 newtons at 8.2 degrees south of east, then you, out of a 20-point problem, you would have got 15 points because you forgot the whole point, which is that it's the equilibrant, not the resultant. You got to stop the equilibrant. And so you could work it all over. You could just do resultant all the way down to the end, and then at the very end just change it to the catty-corner quadrant. So if the resultant is south of east, then the equivalent would be north of west. Okay, on this one, this is in the reference sheets, and 48 reference sheets plus 2 cover sheets are now available PDF. So if you go ahead and download those to your laptop so you have them. And so this is on there, so I wouldn't just ask you to repeat the problem and just copy off your reference sheet. But I might ask you a question about the derivation, like how did Newton get away with making T1 equal to T2 if and not divide by 0? And then you got to kind of explain, well, he used the difference of squares identity, to have them cancel. So in other words, you'll have the thing in front of you, but you got to be able to interpret what's going on. That's the thing. All right, that's higher order thinking skills anyway, rather than a bunch of memorization or a bunch of copying down. Okay. All right, so here is 7 and 8. That's just straight up derivatives. You're going from the first pink to the second pink by taking the derivative. Pretty simple there. Here you're doing derivatives, 2 derivatives, first one being velocity, second one being acceleration. Okay, and we went over these last week. So this was on this first set of practice problems. So just to have this there so you have it. There will be a couple of those on there. Now this one, there's one like this here, and then there's one like this, I think number 20 at the end. So the one on the test Friday will be some kind of mashup between the two. All right, there'll be maybe a little bit of graphing, I was having a discussion in the Zoom with them about either I have them plot the X versus T or I have them plot the V versus T, not both. Like one of them I'll have plotted, you know what I'm saying? So maybe have you plot the V versus T is probably the most likely thing. I don't know, I haven't written this thing up yet. I may not have room to do all the graphing. It may still just be, a lot more like 20 than it is like 13, but we'll see. I do want to throw some kind of graph in there. All right. This one we looked at Tuesday, I think it was, and here it is. So we already showed this to you, and this is also in screenshots from yesterday, I believe. Yeah, so I looked at it over. Anyway, not much to say here. It's pretty much, once again, it's like that previous one where if you said it's above left horizontal. If you said BRH below right horizontal, you're giving me the resultant. But what I want is the equilibrant. So it's catty corner quadrant, equilibrant stop resultants. So, and then of course to find the size 141, you take Pythagorean's theorem. Yeah, you add it, you square the two and add them up and square root. And to find the angle, it's inverse tangent. Okay. This one, yes, I was talking, okay, let me try and repeat what I was saying. I had a pretty good thing to say here. All right, so the question is, why do you do head to tail anyway? Why not just kind of do component method? Well, you can. Component method's actually quite a bit longer, unless you're a whiz at sines and cosines and all that business, stacking and racking and inverse tangents and blah, blah, blah. Now, okay, so on this one, I had a little, I hesitate here because I had a little screw up. There's already a couple things you can say on this. You can look at the air drag and air drags here, and knowing that would tell you that this must be moving. In fact, now my air drag happens to be, I apologize, but it happened to be a little bit off. It was off by about 10 degrees. I don't know what was going on. When I enlarged it, I think one of the axes enlarged a little more than the other. Anyway, I would know that somewhere there's a line of action here, and somewhere along this line of action is going to be my force, my summation of forces. But the problem I have is I don't know how long to make it. Like, is the summation of force this long? Is that summation of forces, which is resultant? And that is resultant, not the equilibrant, the resultant. Is that the summation of forces? Is it this long? Is it this long? So I don't know how long to make it. So that's why you have to do these things head to tail. Okay. And come down here. And when I do a head to tail, and like I say, my RA was off a little bit, my resultant will go from, my summation of forces will go from the very beginning, which is right here, to the very end, which is right here. And that would tell me this balloon is going to go in this direction. If I knew something about the mass of the balloon, I could actually, and I knew a scale here, I could actually figure out how fast it'd be accelerating. Okay. All right, there you go. And then look out for one like this. It'll be on there somewhere because it's really important stuff when you get to packet 5. It's all these free body diagrams. And free body diagrams is the number one thing that physics professors want you to know coming out of class, is how to thoroughly understand free body diagrams. So it's always good to work on those. All right. Okay, on this one, we went through a whole thing. But I'm tell you the truth, I'm getting a little tired, and I got to get this recording out. So, unfortunately, that's just wasted. Well, on 16, Newton's way of doing it, x dot, x double dot, x triple dot is the easiest, the most convenient way. So why ever do it Leibniz method, right? Why do this ddt of dx dt like I have down here for velocity? And ddt means derivative, take the slope with respect to time, which is pretty much all we've done, right, all year, because we spend 4 out of 6 packets in kinematics. That is more than anybody else, I think, probably in the world. You know kinematics pretty well. I don't think anybody's going to fool you on that when you get to college. In your first few weeks of physics in college, up to your first month, is kinematics. And so it'll get you. You'll be really well prepared for that part of the physics class. And then we get into forces. You'll be okay. To me, if you can do, if you can pass my class and think through the reference sheets and all, you'll do fine. Through if you have to end up taking physics in college, you'll get through about maybe the last few weeks. They'll start to hit stuff that you haven't had yet, and they'll go in and do a few things. Every physics class is different. Some professors, what they want to emphasize. I want to emphasize kinematics because that's something I think you can understand. On a visceral level, you can see it, you can feel it, you can do it. But a lot of things in physics you can't really do that with. So I wanted to be able to give you a strong foundation. But so the point is that kinematics is always x dot, x double dot, x triple dot. Which is fine. You can do F dot. If I say F dot, that means dF dt. And that means my force is changing with time, a variable force. Well, we get variable forces. So we do sometimes do F dot, and we'll do a little F dot in packet 6. But we'll also in packet 6 do dF dx. Like, for instance, Hooke's law, how the force on a spring changes. The more you stretch it, the more you compress it. The angrier it gets, the girl on the wall, right? The spring dance. And so force changes with position in a spring. And so that's not dF dt, that's dF dx. Well, you can't say F dot when you mean dF dx. So that is a limitation of Newton notation, that shorthand way of Newton has of doing it. So as long as you're aware of that, you can go ahead and use Newton's shorthand, unless your professor is a stickler for calculus, unless he's a German like Fischbeck was, like my professor was. Anyway, so otherwise you can use the English method, right? But just be careful when you get to certain things. You won't be able to use the dot method. You have to say dF dx. Okay, and then we said, so x triple dot jerk would be a d cubed x dt cubed. And then this other one on 17, I filled that in on the Zoom. And we did it by column. Notice the last column is just the initial conditions of whatever we're dealing with. And then it just, you can work your way up vertically. Look at the pattern. I went in and filled in the coefficients. I just kind of I did this. Not that I'm proud of it, but I did this as an assembly line method, and because that's the way you almost guarantee, you don't think as much, but you almost guarantee you're right, because unless you miss a pattern, if you're off on a pattern, it's pretty bad. So you need to go back and make sure it makes sense. But I noticed that I didn't say crackle knot because crackle knot. There's only one crackles for this series for a sextet. This Snow White sextet, crackle and snow. I put those in the same. Anyway, so crackle is going to be constant. Okay, so it doesn't need to. You don't need to say crackle knot. If you did, I wouldn't count off, but it's just redundant. It's a constant already. So all this can just be crackled all the way up. But these can't because there is a snap. There is a changing snap here. Snap is a function changing linearly with time. Okay, with the slope of crackle. And then jerk changes. So all the rest of these change. So these have to be not. Okay, I do count off if you didn't put those knots on there. But notice snap, not, half snap, knots, 1/6 snap, not 1/24. So the fractions always go 1 over 1, okay, or just the actual initial value, then 1 over 1 times t, then 1/2, then 1/6, then 1/24, then 1/120th. And how did I get that? Well, that's the antiderivative of this. We have to find the antiderivative of this down here. So that's going to be you add 1 to the power, so it's t to the 5th, but then I have to take that into account. So I have to multiply by 1/5, and 5 times 24 is 120. So so you kind of have to go. So up here you have to go backward. Now let's go on to the next one. Okay, I'm just going to cut to the chase. Let me get rid of this, because I'm really getting tired now. This one, I talked a little bit about this. About first, first do this, the envelope, and then I like to color in the area inside the envelope to kind of emphasize, because it's I'm getting old or something, but too many lines on that graph, and so it helps my eyes. And I think it helps the reader too. So yeah, it's a nice touch. I'll probably give you an extra bonus points when you do that kind of thing, on tests. It just shows style, physics style. Style points are important. So then we got to find omega here. And it told us that it was 4 seconds. What we say? It says plot 3 complete, and we have 12 seconds. So 12 divided by 3 is 4. So we have 4 seconds per rotation. And so omega is 2 pi over 4 over the period. And so pi over 2, which is kind of slow. I say slow, but it depends on how big the radius is. You got to get around, you only go 90 degrees every second. So it takes you 4 seconds to go all the way around. So if I was spinning the wheel in front of you, that'd be a very slow spin, pi over 2. And, okay, so then you got to plug that in. You got to plug the damping function in for the amplitude. All right, so here's another one. Same idea, slightly different. Looks like now instead of going to 20, we're going to 4 for our maximum. That's still big. That's 8 meters between oscillations. So this is a really huge clock or something. Pendulum, I guess. This is a pendulum. Yeah, that's a giant pendulum that would take 4 seconds to come back to me. We'll have to time out. I'll put the biggest pendulum I can in the room. That's that's not till packet 6 though when we're talking energy, but maybe we can time it out then. We'll come back to simple harmonic motion at the end when we're talking energy. Okay. So once again, depleting amplitude omega is simply 2 pi over TP, and so we end up with pi this time. So it's going twice as fast back and forth. Yeah. All right. Number 20. Should show you this little by little here. Okay, so let's do ABC. The initial position's right off the equation. For B, you just take the derivative. For C, you just look off that equation and say, okay, well, initial velocity must be 18 meters per second to the right. And then it says, when did it turn around? And we had a big discussion on this, but it turns out that's correct. Quadratic formula is the way to go. I'll try and make the one of the test where you can factor, t minus something, t plus something, whatever it is. It'll be actually t minus, because I'll make both my roots. I'll make sure I make both my roots positive, so we're turning around in the first or fourth quadrant. So we're not into imaginary numbers. We talked about Paul Dirac, and he was interested in imaginary numbers do tell us something about the graph. So it does contain information, looking at negative roots. We talked about there's negative root contains information on damping, things like that. So it does play a role as imaginary numbers. Anyway, but I'll make it so there's 2 real numbers on the test. And then E says, what time will the object reach its highest speed? And that's just set acceleration equal to 0. First, to find acceleration, do the derivative, and then set it equal to 0. And we get 3.75 seconds. And then E says, what's the jerk? You just take the derivative again, and that's 4. Okay. Okay, now we get to 21 and 22. And 21's pretty straightforward. It's, I will, if I have room, I will put those boxes, not coloring them in, but you'll see 6 boxes, okay? And you'll have to fill them in. So, humor me here. That is the standard Leibniz way of doing chain rule. I know you deal with nested functions in calculus, and that's fine. That's another version of it, but that really isn't that, except for sines and cosines, those are nested functions. But a lot of physics mechanics will use the chain rule, but it's really not like you would think as a typical mathematical nested function. something times something. In this case, it's velocity. Maybe in another case, it's acceleration, you know. But anyway, this is velocity. And so we're trying to see how fast that circumference is growing. And we get 94.2 because you have to break up, like for circumference is 2 pi r, and there's no t in there, so you can't take its derivative with respect to time. So you have to kind of sneak t in there, and you do that. You sneak in the t by this Trojan horse. You multiply the right side by dr over dr, and you can multiply anything you want by 1. That's why I think this is a very clever mathematics. Euler, whoever figured this one out. Euler had access to Newton's and Leibniz calculus, but I don't know if he came up with the chain. I don't know who came up with the chain rule. Someone could look that one up. Yeah, somebody look up the chain rule and put that in the group meeting. I'll bring it up in class and I'll give you a stamp. Anyway, so you multiply by dr over dr, and then you split them up. So you split up your fraction. This is all legal. So now, very cleverly, we have dc/dr, which we can do because 2 pi r with derivative with respect to r. This is where, once again, where Newton would not work. Newton's method would not work here because I can't say c dot, you know. C, notice just as a circumference, but say circumference dot is not dc dr. See what I'm saying? So you have to use, that's why Newton won't work here. Okay, so poor Newton, but it won't work here. That's why, you know, chain rule pretty much has to be Leibniz. I don't see the way around it. All right, so dc dt then is dc dr, dr dt, and dr dt is just the velocity of the ants. We said that's 15, so you multiply that all together and you get 94. Don't leave velocity in terms of, or don't leave dc dt. Actually, that'd be okay. If you left dc dt in terms of pi, that'd be okay, to tell you the truth. 30 pi would be fine there, because we do describe circumference in terms of pi. So 30 pi, okay. That's fine, centimeters per second. It's just that it's a linear velocity, and it just seems weird. But for circumference, I could see it. Okay. Now we get down to this one. And this is the piston. And so drawing, you know, drawings are important. I wish I'd looked at my drawing a little closer because I screwed up, but which we'll talk about in a second. But so here's like in a car engine, a piston. This piston is rising, and I don't, someone can look that one up. I mean, you could do the math on that. It's, you know, if you're revving your engine, or say you're at 3,000 RPM, not really revving your engine, but you know, then your cruising speed, you'll do about 2,000 on your tachometer. And if you're dropping into lower gears, like going up a hill, it'll bump up to 3,000. And on my truck, it'll bump up to 4,000. That's when I know I've got to pull in a trailer, and so it's putting too much pressure on it. Anyway, so say you're going 4,000 RPM. The question is, how fast is that piston going inside your, and you can do the math there. Got to look at the length of the camshaft and how, you know, all that kind of stuff. But you could do it. Anyway, so I threw out there 150 meters a second. That's just a fast speed. So once again, I have, 200 meters a second. So here's my boxes, and now I'm trying to find the change in volume with time, but time is not in the function for volume of a cylinder. It's pi r squared times L. So I, you know, sneak in dl over dl and then separate them out. And then I could say d volume dl, which is d pi r squared dl, is just times v, because this is v. This part is v. This part is that. Okay. And I end up with 200 then times pi. But the problem is, r is in terms of inches. We thought we were almost done. Would I do this on your test? Well, I've done it to you twice now. We did once in class on that problem. Now we're doing it again. So, yeah, there's a good chance you could see where you have to do it. Maybe it's not inches. Maybe it's something else. If this problem is on there, this would be certainly blue. It may even turn out to be black. I don't know, but if I decide to go for it and put this on there, I didn't last year. Doesn't mean I won't do it this year. You guys are you're a little ahead of last year already. So I don't know. This would be a challenge to put something like this on. So maybe I'll do it just to see how. I can always go black if I have to. Anyway, I think you can get it down to here, and then it's a matter of now you got to do unit analysis. But I'm liking this problem more and more. Anyway, my problem was in my key, I didn't take the diameter and cut it in half. I went 2.4 and I had changed to 1.2, and we had this big controversy. And then at the end, after did the recording, I went back and did the math, and sure enough, I agree with Owen. I think was it Owen? No, Trace. One of those guys were the first ones to say it's about 580,000. Okay, 3 SIGs, 583,000 cc's per second, cubic centimeters per second. That is how fast it's decreasing. The question was how fast is it decreasing, the rate. So if you made it negative, I'd understand, but tell you technically it should be positive. That's the way the question's worded. Okay, here's the 23, the last one. I apologize on part E. Oops, sorry. E, I don't know why that got cut off, but I fixed it on the key. You can fix yours. All right, so let's start off. This one's undamped, thank goodness. Damping, then you got to multiply through, and the power chain rule and damping don't go together very well. Anyway, so we're looking at I can plot this up because I can figure out the TP just 2 pi over omega. So TP is a half a second. I'm supposed to do 2 seconds worth. And I know it's cosine. It says it's a cosine oscillator. All right, there's no reason to assume negative cosine. So the default is positive cosine. And then just carefully draw your, whenever I'm drawing those, I always do it. I always scaffold it out. So like on this one, let's see. Okay, I end up back here. I got here and here. So I always go through and then I do the bottom ones. So I know where I'm going to kind of keep me honest. If I don't want to end up with something like this where it kind of like that. No, you're going to get no points for that. So you have to be accurate. And I go ahead and I do these, maybe the up ones first. I'm left-handed. And then I do the other side, the down ones. And that's not good. I should start down here. Because then you hit that point of inflection. You see what I'm saying? Little trees over here. Very nice. Okay, happy trees. These are happy cosine waves. Okay, so Bob Ross, of course, Bob Ross. So you have the equation. So far with part A, nothing really weird happened. We have a maximum. One thing's weird. We are going back and forth awful fast if it is plus or minus 3 meters. So 6 meters, that's 18 feet. That's from wall to wall. That's the front wall of my classroom to the back wall of my classroom. And so I've got to get back and forth. I got to run from the front wall to the back wall and back to the front wall in a half a second. So this is some kind of, what does it say? It doesn't say what it is, but it's some kind of a oscillator, a big, like in the cruise ship or something, some big, huge piston going back and forth. I don't think, to tell you the truth, I don't think any large, the problem with it is we're going to find with acceleration is the G-forces. And I don't think any large, although pistons in a car takes a lot of G-forces. We always think G-forces, any G-force above 12 seems, you can't go above 4 in a roller coaster, 4.5. So when you talk about, the Apollo astronauts undergoing 12 Gs or when John Glenn undergoing 16 Gs or poor Stat 42 Gs, I mean, that seems inhuman. And the amount of G's we're going to find here on this one is going to be really big. So no human could survive this, obviously. But for a machine, it can survive a lot of G's. Doesn't matter. We're going to pass out. We pass out because the blood leaves our head, depending where our feet are, or we have a stroke. If we're going the other way, you get too much pressure in your head and your veins and your brain pop. So anyway, but anyway. So we're assuming it's a machine, not a human. And so then on the next one we get this weird 38. Like, where does this 38 come from? Right. Okay, where does this 38 and this negative 38 come from? Well, that's maximum velocities. And that's the amount of velocity you have to be able to run. For me to run back and forth from the one wall to the other wall, I got to be running at 38 meters a second, which is almost 4 times the fastest human. So a machine could do it, though, right? A car could, but a car could not. Even a Tesla. I don't even think a motorcycle. Maybe a motorcycle could do. It can't. Thing is, it can't turn fast enough. That's the problem. So yeah. So this has to be like a piston or something, a big one. Okay. So notice that when I'm at equilibrium, and equilibrium is here, here, here. My velocity is at a maximum because I'm going through equilibrium. And that's where the thing, like a pendulum, that's where it's going the fastest, through equilibrium. So those all line up, and that's a quick check. And then the reason why I get that 38 is the chain rule. And I would be okay if you put 12 pi there, but you don't really talk about velocity, and you never talk about this is really linear velocity. You never talk about velocity in terms of pi, okay, unless it's omega, where it's rotational velocity. But linear velocity, it's kind of a faux pas to talk about that in terms of pi. It's just laziness. I would take it, but 38's a better answer than saying 12 pi. Okay. Well, we do it again. We do the chain rule again, and now we have accelerations. And this is where we get these astronomical, what I was going on and on about earlier, was those numbers. That's meters second squared. So that's 47 Gs, or over 47 Gs, that no human, could. Yeah, humans have probably had those kind of Gs, but that's when they, got blowed up real good or something. That's when. Maybe when you slam into a wall, you're undergoing snap kind of stuff. But anyway, so you're being jerked around pretty good here. So no human's going to do this. Notice that, so it's a machine, but notice that when I am at 0 velocity, let's do this little tag game again. When I'm at 0 velocity, I am at maximum. And that's so it's weird. There's no velocity, but you're at maximum acceleration. And what this is called a resistance. We didn't talk about this. We'll talk about this more in packet 5. But springs deal with something called restoring force. Here's a recording special, a restoring force, and restoring force. They're always like we're going to find Hooke's law eventually, and that is the force of a spring equals negative kx, and the negative there makes it a restoring force. And what's it trying to restore? What is the girl on the wall trying to do? She's trying to get to Herona. She's trying to get to nirvana. All girls go towards Herona. So Herona's in the middle. He's nirvana, but so all girls gravitate towards Herona. But they miss him, and they come back. They get more. The further away they get from him, the madder they get, and they come back. But their sweet spot, where they want to be, is with Herona, and that makes no sense unless you look at my wall and see that some wag taped Herona's picture at equilibrium. All right, so someday that'll make you snicker. And then notice that when this gets here, when the velocity is maximum, acceleration is 0, because why would the spring or whatever's causing this simple harmonic motion, if it wants to get to equilibrium, once it's at equilibrium, why would it want to keep accelerating away? It's trying to get back to equilibrium. So it makes sense that you can think of the acceleration as the desire to get back to equilibrium, and increasing the acceleration means there's an increased push to get back. Well, once you're at equilibrium, you would expect to be at zero push. And then, sure enough, because of inertia, it blows right past equilibrium. And then we're back at zero velocity. Now we're at the other side, which links up to maximum anger, trying to get back to equilibrium. See? So back and forth. And a lot of anger. Look at that. Yay, yay, yay. Okay. That's it. Good luck tomorrow. And this recording's done on, just for completeness sake, this is done on, what is it, January 25th, I think, 2023. This is ASCII Physics.